Hello everyone. Welcome to our let me see. I think fifth session or fourth session. Uh, as a part of the ZK month. So the ZK month is a series of sessions where we are going to be covering different protocols. We are going to start with snarks and starks, which are the basic algorithms. And then we will also have invited a couple of speakers from different protocols to talk about how they're using the concept of zero knowledge proofs and building what they're building. And today's session, we are going to focus on this topic called Circom. We'll not go too deep into like snarks or like the proving side of things. And we'll just focus on learning how to write circuits in Circom. There are multiple reasons to why we want to learn Circom. One of the main reasons is Circom helps you have granular control over what kind of constraint system you want to build. So all of the protocols, rather the proving protocols that are used in the proof systems are built on top of constraint systems, right? Why are they built on top of constraint systems? Is that whenever a prover says that I have done this and sends the proof to the verifier sends some sort of inputs to the proof to check whether they are getting the expected result or not, right? And all of this happens in the form of mathematical constraints. Like you can create a proof, and that also has some constraints. And when you are trying to verify the proof, also there are some constraints associated with it. So when you're largely, especially when you're trying to generate a proof, right? So this Circom helps you write circuits at very granular level in order to build constraints, in order to build programs basis these constraints. So it is a very useful language if you are getting started with zero knowledge proof systems. And the second thing is why I think it's important to learn Circom is it helps you appreciate other programming languages that are coming up, because Circom is so close to being such a circuit oriented, such a like a wire based language, that when you decide whether you want to spend time learning other programming languages or not, you can always think about, hey, what can I do in Circom versus what I can do in this programming language? And you will find a huge difference, right? And I'll tell you a little bit about how that is. So what is Circom? You can think of it as a programming language or a circuit based language which helps programs program constraints to build circuits. And these circuits are the ones that are used in zero knowledge proof systems, mostly snarks in this case, to create proofs. And the arithmetic circuits that are built using Circom operate on something called signals. So this is the very base of what Circom is all about. That it expects you to send some signals into the Circom code, and then you can have an output from the Circom code, which is also in the form of signals. Okay, I'm going to. Okay, all right. So this is very important because everywhere you will see a lot of this terminology being used, signal. So think of signal as the variable in Circom. So the arithmetic circuits that are built using Circom operate on this concept of signals, right? So let me first show you Circom. Okay, sorry, close other tabs. Okay, so if you go to Circom, the recent version of Circom is Circom 2, and the documentation is, I would say it's okay. I don't think it's up to the mark, but well, you've got to do what you've got to do with what they have. And for beginners, it's pretty good. You can see that you can use like Rust you need some sort of Rust modules to install Circom, but it does that internally itself. So if you open actually the Circom repository, the GitHub, you will see that a lot of underlying scripts are written in Rust, and it's pretty interesting. But it's very straightforward to install Circom. You can just clone the GitHub repo, and then you can basically you need Rust. So it uses cargo build release to do this, and then you say cargo install path circom. And once you have installed, you should let me share my screen with the terminal. You should see something like when you do circom hyphen hyphen version, you should be able to see the. All right, terminating all instances. Window. Okay. So if you do Circom version, you should be able to see what is the latest compiler. So Circom has been there for quite a while, from what I understand, and it has gone through a lot of different versions. The recent one is Circom 2. So we'll be using mostly Circom 2 in our today's program. And there is another important concept in Circom that you have to understand, that how it implements these circuits is by creating these constraints, right? So I'm going to show you a little bit about these constraints. And these constraints is what will help you understand how to write these Circom circuits, right? So you are actually the mathematical constraints that are used to create the proof. You are trying to program these constraints, right? So you need to be able to generate these constraints in Circom. So what are the different ways in which you can write pieces of code in Circom, right? What are the different things that are allowed in Circom? And let me tell you, Circom is a very simple language. It is a very limited language. It doesn't give you the ability to do things that you can do otherwise in different programming languages. Like you can't have like if else, and you can't have like branching and things like that. You can have loops, however, and you can just do like some basic addition multiplication. You can't have too many complex operations within Circom. And these are some of there are just few things that you can do in Circom, which I will show you now. And then when we start writing some Circom code also, we will see how that is done. So the first thing is you can have constants in Circom. They call it constant constraint. I'll refer between this presentation and the actual documentation as well, so you can understand a little bit better. Sorry. So only a constant value is allowed. So you can define a constant value by using the var keyword, and you can see that you can basically assign a 1 or 0. So you can have var the name of the variable is equal to 1 or 0. I'm not exactly sure if you can define other values to it, but from what I understand, you can only do a 1 or 0 constant. I believe that there are some other values that are allowed, but there are some bit constraints as well uh, that I will show you in some example codes that we will go. So if you want to just have a constant value, it is allowed to have in Circom. So the slides that I'm going to go through are different forms of expressions that Circom allows you to have. So the next one is called a linear expression. So linear expression is basically something like adding two variables, or multiplying two variables. So any form of linear expression. So you can see here that there is a input variable and there is another input variable, and you are adding both of these, and you are getting an output. This is actually, it should be written like this in Circom if you're assigning a signal, but I'll come to that later. So just to know that these are like linear expressions that you can have, which is you can express these linear expressions using addition or multiplication. And here are some examples. So this is like a constraint where you're saying that this particular expression should be equal to 0. So you're checking for that constraints. And if this is not 0, then this circuit will just fail. And this is E2 is a constant. So you are multiplying some sort of input signal into with a constant, and you are giving that as a output with, and you're adding it with another constant. So this is another linear expression. So linear expressions where basically only addition is used. You can use multiplications, but it will be something like this. Yeah. So because these additional multiplication with constants is allowed. So something like this. I think this maybe results to a constant. That's why it's allowed to. The next type of constraint or expression that you can use in Circom is multiplication. So multiplication between a quadratic expression. So multiplication between two linear expressions and addition of a linear expression. So something like a into b minus c. So the example for this is you have this one linear expression, which is 2x plus 3y plus 2 into x plus y. And this becomes a quadratic expression, but the second one, you're just adding it, so it still remains quadratic. That means the maximum power of a variable can be 2, right? And these are the only three types of expressions that are allowed in Circom. And anything else where any arithmetic expression which is not of the previous kind, which is non-quadratic expression, and Circom compiler will throw an error saying that this particular expression is not allowed because it is non-quadratic. It doesn't it doesn't understand any other type of expression. And that is basically, these are the different types of expressions that Circom can have. This does not mean that this is the control flow of a Circom program, right? These are the different ways you can use variables within a Circom program. This is what it means. Now, okay. So what are the different ways you can create constraints in Circom, right? So when you're saying create constraints in Circom, what it means is you are saying that a combination of different signals that has come to Circom, you are performing some logic on that, and then you're saying that these particular signals should behave in a specific way. So you will have some input signals coming to the Circom, and you will have an output signal that will be sent out from Circom, and you can try to add some constraints to the input signal to make sure that you're able to prove your statement. For example, if you have to prove that you are sending two inputs and one input is greater than the other, then you can add some constraint to those two inputs and send the output as yes or no, whether this statement is correct or whether variable 1 is greater than variable 2 or it is not. So you can create constraints on your inputs using certain expressions. So what kind of expressions that you can use to create constraints? There are three types of expressions, and only these three types of expressions that you will see when it is associated with constraints. One is this symbol, which is triple equal to. So triple equal to is basically a simple constraint where you are asserting that this particular expression should be equal to this particular expression. That's it. It's very simple. So you're just saying LHS is equal to RHS, and you're adding that, you're imposing that constraint. And if this statement becomes wrong, then this code will exit at this point in time in Circom, right? And it will fail. Now you have another way where you can combine with a signal, you can combine an assignment with the constraint. So what you're doing here is that you are creating a constraint, and instead of that third equal to, you use an arrow which you use for assignment. So here what you're doing is you are saying that 1 minus a into b, the value of this is actually being assigned to out, and you're constraining, the constraint here is that out will always be assigned this value only, whatever is produced by this 1 minus a into b. Now how do you, so whenever you read the output from this particular Circom circuit, based on the value of out, you can decide whether your particular proof was, whatever the statement was, has it been successfully proven or not. So there is a third symbol that you have to remember, which is arrow and then single two hyphens, not equal to, but hyphens. This just means assignment, which is, there is no constraint associated to this. This just is used for assigning the value to a signal. So this value is being assigned to this. That's it. The difference between this statement and this statement is that over here you are saying that out will be constrained to be this value. You can't change the value of this signal. However, in this, you are saying that I'm just assigning a value to this, right? And then you can, if there is a need, then you have, if there is a need for this to be constrained to this value, then you have to use something like this. So generally, you will not play around with assignment for signals, because for signals, you want to use signals for constraining, right? So you want to make sure that input signals, you do something and then you have an output which is, some sort of constraint with respect to the input signals. So you generally use this when you are having some sort of constants, like when you're using some constants and you want to use those constants for doing something else in, or you are creating signals and you want to use those signals for doing something else, like some extra variables that we may need in the middle of our circuit to perform some other operations. So at that time, we may want to create a signal and use this assignment operator. But generally, it is advised that don't use the assignment operator on your main signals, like your input signals, like your output signals, right? Use always constraint based operators. So, for example, here, this particular template that they've given, which is multiplication of three inputs, you see input one is a signal, input two is another input signal, input three is another input signal, right? Now, this particular template they have given to show that this piece of code is wrong, because you can't have three signals multiplied with each other. This will fail because it is non-quadratic constraints. So you may have to have some middle variable in which you store the value of the multiplication of first two signals. Then you take that variable, multiply it with the third one, and then you give that to the out. This is why I said you can use these assignment for some middle signals, but generally don't use it on your main signals, because you want your main signals to have the logic that you want to carry with your program. Now, these are the main type of expressions that you will see in any Circom circuit. Now, let's take a look at a simple example circuit. Okay. So you will see this generally as a common example of Circom, which is a multiplier circuit. So this circuit template checks that C is the multiplication of A and B. So when you think of this from a zero knowledge proof sort of context, what happens is you are providing two inputs, right? And both of these inputs that you provide to Circom, all of the input signals will always be private. And this is where your concept of zero knowledge comes into picture. That when you're sending inputs to Circom, these inputs are always private inputs. However, all the output signals are always public. So anyone will be able to see the output, but people will not be able to see the input that was sent to the Circom template. And how all of this happens, we will see this in a later like theory session and stuff. But this is the whole idea, and this is how Circom helps writing circuits that can prove, zero knowledge, that can create zero knowledge. So if you see a simple Circom circuit, you see it starts with pragma, which is telling the compiler which version of Circom should be used. And then you start with writing your Circom circuit itself. Now, so in generally Circom circuits, you will see most of the circuits having this format where they're writing in the format of a template. So what this means is that when they're writing a template, this template can be reused anywhere else, wherever you are, you want to say, for example, have a two number multiplication. Once you write a template and publish it, you can use the template wherever. However, to invoke this particular circuit, you need to actually call this template, right? So you can call this template by using a keyword called component, which I will show you shortly. But that's the idea, that you can you can write circuits in the form of templates, you can publish it, and these templates are reusable. Now, how do you write a simple Circom circuit, right? You start with a keyword template, you write the name of your template, open close parenthesis, and then you open your curly braces within which your template code will lie. The first thing is you will have you will write a declaration of signals. That is, what are your input signals and what are your output signals. So you have a signal input A here. So like I said, each variable in Circom is a signal which you are going to send. So you have input signals and output signals, and then you'll have some intermediate variables as well that you can use temporarily if you want. And then you can also create your own new signals, which don't have to be input or output, but just intermediate signals that you will use. So when will you use signals versus variables when you're creating intermediate variables? You will use signals if you have to store the assignment operation of some other signals, right? Otherwise, there'll be variable mismatch. And you will use variables when you just want to use, like, say, 0 or 1 or something, like some values that you want to use. So in this case, we have two input signals A and B and one output signal C. And the constraint is that, and the problem statement is, this circuit template should check that C is the multiplication of A and B. So we are just adding a constraint C, which says that C will always be the multiplication of A and B. So every time you are sending two inputs A and B and you read the output, it will always be the multiplication of A and B. So this is a simple, like, Circom circuit. Most of the Circom circuits will be like this. They will be whatever logic that you are trying to write, you will have to try to convert the logic into a mathematical format, because all of the Circom circuits are actually arithmetic circuits. So if you are saying that your problem statement is to check that someone is above 18, right? So you will have to create a circuit in a way that you're sending two inputs. The first one is a private input, which could be the original age. And the second input could be the actual number, which is 18. And then you create a constraint to check whether their actual age is greater than 18 or not, right? A simple example. So any problem statement that you are going to try to write a circuit for in the zero knowledge, want to create a proof for, you will have to try to arithmetize that in order to fit it into Circom. Circom also offers other types of circuits. Like there are circuits for, like, hashing and things like that. But those also are having some constraints. So let me, okay. So I just want to quickly show you. I think I've already shown you assignment and constraints. So the first one is assignment. Sorry, I have 3 hyphen. It's actually 2. And these two are constraints. This one is just like checking for equality, like an assert statement. And so this, if this goes wrong, your circuit will just stop. And this is an assignment constraint. So this is just an assignment. This is an assert constraint, and this is an assignment constraint. So before we go into writing Circom, which is our next step, how do you look at building, end-to-end products using Circom? So there is another library called Snark.js that helps support building your end-to-end dApps using Circom. So let's look at the image first. You have a high-level circuit description, which you go through, which goes through the circuit compiler, Circom, and then you get the low-level circuit description. So you run your actual circuit. This itself, what we are writing, they're calling it high-level, your arithmetic circuit, right? And then you compile it to using Circom to get a low-level representation. So you will get something called rank 1 constraint system. So R1CS, as you can see, like, you compile the circuit to get a low-level representation. Then you send this low-level, you use these parameters that you generate from here. You have an R1CS file, you'll get a WASM file, and you'll get a SIM file. So using these files, you write your any JS, you take a JS file and then you import your Snark.js library, and you compute something called as witness, right? So you calculate the witness for the different files using the different files that you have created. Your WASM, your the input.json is actually your inputs that you will be sending to your to your file, and you calculate something called as witness. I'll not go too much into this. We'll do this like in the theory part of it. And then once you have this witness, you will use this witness. You will have to generate a trusted setup and get the proof. So you can you can use your own trusted set of files. Generally, the popular trusted setup ceremony is called Powers of Tau. So you can use those files and you can generate the proof. Once you have the proof that you have created, you can validate that using Snark.js directly, or you can also generate a verifier contract using Solidity to verify your proof. We will do this itself as a separate session that will be taken as a hands-on session where you will be using your Circom circuit, you will be using Snap.js, and you will be building a small application. So because we're going to have that session, I don't want to go deep into it, but I just want to let you know, like, what do you do after? What we are going to focus on today is just this green part, which is the Circom circuits, right? So let's get started. For actually writing Circom circuits, you need to have Circom installed. Let me share this again over here. Once you have Circom installed on your terminal, when you do Circom -- version, you should be able to see the version of your Circom compiler. Okay, I have a lot of stuff. Okay, I wanna. Okay, I'm gonna give you one repository. So here is a repository that I am going to share with you, and I'll share this later after like our session as well. And you can clone this repository. We'll just do a few circuits from this repository, right? There is also another very interesting repository that I'll share with you later. And maybe I will show you the code of that if I have time, if we have time. And yeah, and then we can. Okay. Does everyone have Circom installed? Ovia, you were facing some problem installing Circom, no? Were you able to resolve that?
No, Gyan, but I think it is because of my laptop.
Oh, I see. Okay, okay.
I'm still not sure. Maybe I'll try with somebody else's laptop and then come ask you. It's a
Okay,
problem.
okay, okay, no problem. Okay, so maybe just to interest of time and because it's also like a late-ish session, I'll just start going through. I wanted to share one piece of code that I will show you here. And then we will do some like we will write some very small pieces of Circom circuits. And if you want to like know how to write your Circom circuit, like, I already have this repositories, but you just have to say like, you can just create a file, which is like let's say a new file. So you can just plus over here and then you can just say like whatever add.circom. It opens a new one for you and then you can say pragma 2.0.0 and start writing basically your code, right? And then you can create a main component and then say that main is equal to add, right? So this is a simple sort of way to write your Circom circuit. It's very straightforward. You just open a new file .circom, and I will also show you how to compile your Circom code. Right now, I already have some Circom files, so I don't need to create one. But if you want to, you know now how to, right? I'll just walk through this piece of code because this has almost everything like that I want to show how to write in Circom. And then we will start writing like at least some one or two small Circom circuits, and I'll give some more Circom circuits as homework. So, okay. So this is called repeated square. So what this circuit is doing is it is taking an input which is n, and then it is saying that you repeatedly square this input x n times, right? And the final output will be the repeated squaring of x n times. So that's the problem, right? So you are saying that the final output should be the equal to the repeated squaring of n, repeated squaring of the signal n times. That's the you're proving that, yeah, the final output is indeed this. So how do you start? You start with the keyword template and then the name of the circuit. And because this takes a parameter, we just give the parameter. There's no type or anything to this parameter. It is arithmetic. There is no other type to this. So it's just arithmetic. So it's a number. It's a numeric parameter. And then within your open close braces, curly braces, you write your template code. So we have an input signal, which is X. So we say signal input X. This means whenever you say input, that signal will always be private. And then we have an output signal, which is Y. So you say signal output Y, and which is always public. You can have uh, you can have as many input signals as you want. I don't think there is any constraint on the number of it, but I'm sure, like I'm sure the more heavier your circuit is, it probably takes a while to generate proofs and stuff like that. So from a proof generation perspective, there might be a constraint on the number of signals that you can have. And okay, so you have an input signal, you have an output signal. Now, because we need to have this repeated squaring, right? We are going to have a intermediate array of signals in which we can store this repeated squaring, right? And then because we need to store at least n squarings, right? So we are going to create an intermediate signal called xs, which is x squared, and the length of that is n plus 1. Now the zeroth signal, the zeroth is the one that we are going to assign the value of this, assign x to this. So we are going to have the input value will be assigned to the zeroth element of this array. And then in order to create the squaring, what we do is we use a for loop. So we are going to create a temporary variable. This is var. So var is the keyword to create a temporary variable. This is a signal. So I told you, right? You can either have a temporary signal or a temporary variable, intermediate signal and temporary variables. You need signals because when you're computing with other signals, you can't store them in variables. However, you can use variables to do arithmetic stuff, like going through different array indices and things like that. So that's the difference. And that's how you have to figure out if you want to have an intermediate variable, should that be a signal or should that be a temporary arithmetic value. So we have a signal xs with size n plus 1, and then the zeroth one is values x. And then we run through a loop between 0 to n because we want n squarings. And we just say that the I plus 1th element, that is the next element, is going to be multiplication of the previous two elements. That is the square of the previous element. That's it. So this is an extremely simple circuit. And the final thing that is in the problem statement is that the value of y, the output should be the n times squared, right? So the value of y will be excess of n. So every time you will see that whatever value that you want to define as the output, like something of 2, something of 1, array of 1, 2, etc., you will see that the array size will always be n plus 1. This is from my understanding, so that there is no spillover or something, and so that there is enough allocation. Or it is probably because if you define n plus 1, it allocates for n. But yeah, so like for example, if you are using a 3 inputs, then you are likely to define an input array as a of 4. So something like that. A of 3. So you 0, 1, and 2. Yeah. Okay. So this is a very simple repeated squaring circuit. Now, if you go to this other second repository that I sent you, which is a zero knowledge puzzles, here are a few few circuits that we can work on. And I'll also show you some more circuits which are part of this library called Circom lib, which Circom has already published, that we can use. Actually, let me show you that first. if you install Circom or if you clone Circom, the Circom GitHub repository, which also let me share with you. Okay, Circom lib. Okay, so if you clone this repository, which is the Circom lib repository, you will find all the sample circuits, all the circuits published by the IDEN3 team who created Circom. And there are lots of helpful circuits here that you can use for your programming logic. You can also write these circuits on your own, and we will be doing that, for some of them. But you have different circuits like comparators. This is a very commonly used file where you have different comparisons like is zero, do you have is equal, you have force equal if enabled. So you have different type, less than, greater than, and stuff like that. So this is a very popularly used, you can use this state and actually uh, add that in your logic. And then you have different types of circuits like EDDSA, sorry. So you have this EDDSA verifier circuit, like in terms of how this works, how the EDDSA algorithm works, that is implemented in the form of a circuit. You have gate circuit, you have MIMC, which is another popular hash, which is also implemented as a circuit. You have multiplying of 1, 2, 3, 4 different types of circuit. Peterson dot Circom. Peterson is also another hash, Peterson hash, which is a popular hash. Again, you have that circuit of Poseidon. So you have different types of circuit. For beginners, I would generally say go through the mux circuits. They are just multiplication circuits, and then you can go through the comparator circuit. You may use sometimes the binary sum, binary subtraction circuits, but not very commonly. So the more complex your problem statement is, you may want to use more complex circuits. There is a signature circuit and switcher circuit. I don't know what, to be honest, I don't know what they do. But you should be able to find it in the documentation. So for some of our circuits, we may use the help of other circuits, but otherwise we should be okay just writing the circuits from scratch. So in this one, the first circuit that I wanted to sort of write is the addition circuit. You can see that their repo is fairly new, so they have used 2 dot, it's 2.1.4, a slightly different version from what we are using, but it should be okay. So now we will write 1 or 2 circuits just to get an idea of how you sort of perceive the problem and how you start writing circuits, the idea. And I'll share more of these that you can do as homework. And of course, I share the repository thing also. So in this exercise, you need to create a circuit that takes an array A of length 2 as input and an output C. So when they say you need to take an array A as input, so we say signal input and A, and the array will be of length 2. Okay. And you need to take an output, or you need to define an output. So we say signal output C. Create a circuit that adds the 2 inputs and outputs it. So we can create a very simple one-line circuit. So here we have to create a constraint that the addition of the first 2 elements in this input A should be equal to C. So we say A of 0. That's it. Right? It's a very simple circuit because here, if we just do this, right? This is not correct because here we want C to always be constrained to be the addition of these first numbers in the array. Okay. So this is a simple circuit, very simple. And then if you want to call this template, like I said, you have to create a component and then you assign the add to this component. And whenever you're using your snark.js, you will call this component. When you call the main component over here, then it will refer to add, and you can send the you can send the inputs to the main component, and when you read the output, it will be the summation of the first 2. So this is a very simple circuit. And if you want to compile this, you can just do Circom and the name of the circuit, and that's it. So let's see another one, which is equality. Okay. Okay. So this needs some sort of let's do range. I'll go to that because it requires you to have another circuit over there. So we'll take that. In this exercise, we learn how to check the range of a private variable and prove that it is within the range. So this is a simple example that you can use in any application, right? You can, for example, in KYC based application, if you want to check that a person meets the age criteria of a certain range. So you take the person's age as a private input, send it to the Circom circuit, and then make sure that you are getting an output as 1 or 0, right? So, okay. So here it says declare three input signals, A, lower bound and upper bound. So I'm going to say signal input A, signal input. Okay. And then it says if A is within the range, output 1, else output 0, using out. That means I have to have another signal, which is the output signal called out. Now for this, I can directly use the comparator circuit because I want to use the less than greater than circuits. So I'll show you that. Okay, so in order to bring the comparator circuit, I need to include it. Oh, I've already included it. So I have to include the comparator circuit. So I go out and I go to the path inside node modules under circumlib circuits. I have the comparator circuit. Now let's open this comparator circuit so I can show you. Okay. So you have in this a template called less than, right? So the less than template takes that the first number is less than the second number. It will have two inputs, right? And if that is true, the output is 1. And if that is not true, the output is 0. So here it will take two inputs, in of 0 and in of 1. So what we are going to do is we are going to create a component here called less than, which is equal to less than from comparators. So we can directly write this because we have already included the comparators Circom over here. Now what we are going to do is we are going to assign the both the inputs to this less than. So we are going to say less than dot in of 0. Okay, so we are going to check A with upper bound, whether A is less than upper bound. So I'm going to send the first input as A, and then okay. So there is going to be an out also from here. I will use that later and I'll tell you how I'll use that. Now I'll use the up greater than component. So there is a component called greater than, which you can see over here, which makes sure that the first number is greater than the second number. So I'll call this one the creator component. I'll say greater than dot, I'm assuming it's input. So the name of that should be the same as the name that is given in this circuit. So if this circuit had something like A and B, we should do here as less than dot A, less than dot B. But in this circuit, the names are IN, that is input. So IN 0 and IN of 1. So here I'm going to say, so I'm going to check if A is greater than the lower bound. And now I have to assign, I have to either have like 1 or 0, right? So if A is within the range, output 1, else output 0 using out. So what I'm going to do is I'm just going to say less than Okay. Okay. So here I'm just saying that if both of them turn out to be like if it mismatches either one of them, that it is so it will either one of them will come to be wrong, right? So it will when we do the difference, we will if we get 1, that means A is not within the range. If we get 0, that means A is within the range. So we are just using some logic to make sure that we assign either 0 or 1 to out, because we can't have an if branching in the code. So we have to make sure that we have some sort of arithmetic logic to make sure to assign out in a way that it results in either 1 or 0. So this is another sort of simple circuit, not so simple, but you basically understand like whether it is. Hey, yeah, Ovia, you raised your hand.
Hey, again, do you mind repeating this again? I didn't get it. So if less than is false, if let's say the first one is false, it will give the output 0. The second one is also false, then it will give output 0. And 0 minus 0 is anyway 0.
So
So
it will be only one of the, so it won't be less than, or like basically it will only either of these conditions will be false at a time. It can't be both less than and greater than, like the
so we're
given.
checking different values, right? The first one is checking with A with the upper bound, and the
Correct.
second one is checking the A with the lower bound. So it is
Correct.
possible that both can be false.
Uh, no, how can it be? Like it will, if for one of them is false, then the other one will be true, right?
No, what? Okay, right.
Say, okay.
I'm just thinking of an example. 1 second.
I'm also thinking of an example. Okay, if A is like, oh, also I think 0 signals are allowed. Okay, if A is 0 and the range is 1 and 2, or 1 and 3, only 2 falls in between. So A is, so one of them will be true. Like A will be less than the lower bound. Like if you see, you got it. Like,
Can you consider this example? A is equal to 2.
mm,
Um, lower bound is 1, upper bound is 3.
yeah.
Okay, so first one you're
Okay.
checking if A is less than. Okay, sorry. The other way around. A is 2, upper. 1 second.
So see, A will fall either here. So it will satisfy one of the conditions, that it will be less than the, like, just imagine on the scale. Either A will, for the condition to go false, either
Mhm,
A will fall before both the numbers. In
mhm,
that case, it will definitely satisfy the upper bound condition,
mhm.
or it will fall after the scale. In that case, it will definitely satisfy the lower bound condition. The only way it will like it will get 0 0 is it will get 1 1 is when it is in the center.
Yeah.
These are not
Okay.
floating numbers, right? So only either or, it will definitely satisfy, like as in one of them will definitely be one.
Okay. Yeah. Agreed. But
So
again, this is if it the second one is the one, then it will be -1, right? There's
it will
negative.
still take it as a one signal only. So I think -1 it will take as a analog signal as like high voltage.
Okay.
Yeah. Okay, yeah. So basically, we have to try and arithmetize our logic to make sure that we are able to satisfy the signal properties. Like over here, we can't do like if this, then do that, if that, then this. But you have to make sure to have like logics like this, where you can have, be able to generate some signals from this. So this is like a range circuit. This equality circuit is a little bit dicey, so I'm not doing this. There is one very other interesting circuit that I will show you. It's a completed circuit, but I still want to. It's a little bit complex. This one, Sudoku. Um, Circom.
Gyan, one more question.
Hmm.
In one of your earlier circuits, you showed a for loop, right?
Mm-hmm.
And that for loop had a less than, and the compiler is able to do the less than in the for loop, but it is not able to have less than constraint.
Yeah, because it's not able to have like constraints between signals. It can't have like so you saw the expressions with signals are limited. You can do things with inside which are like constants. So if you see the for loop, it is just a variable. I don't know where that. I think comparators or somewhere. So the for the for loop we just use like variables, so that is okay. Between variables we can do, but it is not possible to have these kind of things with signals. With signals, the things that you can do are very limited. You can either add the signals, you can multiply the signals. That also at max you can only multiply two signals, which is a quadratic restriction. And you can have constraints on the signals. These are the only things you can do like in this. So if you see, the for loop is on the constant variable, which is, yeah, I mean, they call it constant. So basically, yeah.
But n is an input signal, right?
No, n is again just a number.
Okay.
The signal here is x and y. So you can't do anything with on these except multiplication of max 2 and constraint generation like this. Okay. Sudoku. Okay. Okay. So I this will be the last thing that I just want to quickly run. And the Sudoku problem is a very common problem that everyone uses to talk about computational integrity. What that means is how do you prove that you have computed something, with integrity without having to actually prove what you did. So the Sudoku problem is a very standard problem, and this is a very like rudimentary thing of the Sudoku problem that I have the circuit for. There is a more complex one also that I can give you as homework for those who are interested. But basically, the Sudoku problem is a problem that you are going to check whether a particular solution that the solution that will be given will be private, and that particular solution that you're giving is that correctly computed or not. And we know the rules of Sudoku that all of the rows have to be distinct, the columns have to be distinct, and then when you see the first nine sort of the boxes, you see that that also has to be distinct. So it's a 9 cross 9 grid, and all the rows and all the columns have to be distinct. That's your problem statement in Sudoku. And what they're doing over here is the main circuit is the template Sudoku template. This is the n is for 9, which is the 9 cross 9. But essentially, you can actually do whatever. You can use this for doing 4 cross 4, 16 cross 16, or whatever. So here, the solution is a 2D array, and you take the signal as the input signal as a solution. So that's a private signal. You don't actually know how that person has solved it, which number is where, but you're still trying to prove that yes, this person has solved it successfully. And the puzzle signal is the initial puzzle that is given to them, where you have some numbers that are filled, but wherever it is zero, it indicates a blank. So I'm not going to write anything in the circuit. I'm just going to go through the circuit, because writing this will again, it's just the Sudoku logic. So I want to focus on Circom here, how Circom is written. So the puzzle is the initial piece that is given to you, where zero indicates blanks. And then we have some things which I will explain what these are and why they are needed. So first thing what we are doing is we are checking if we are going to loop between the rows and the columns, and we are checking that the puzzle itself, right? That you are basically checking if the puzzle itself is filled, like the puzzle is you see whether the um, each element of the puzzle is filled or not, right? So you're checking whether the puzzle is proper or not. And this is just a simple thing. So what they are doing is they subtract the puzzle element with the solution element. So if there is a solution that is there, so what you're checking is whether the solution is the solution puzzle that you got, from the existing puzzle, are the numbers that were there in the older puzzle, the same numbers are present in the solution puzzle at the same places. Like if your existing puzzle had one, some 0 0, which are blanks, four, then zero, something like that, you're checking whether the solution puzzle has one at the first place, a space four at the second place. So you're checking whether the solution puzzle is built on, mapped on top of your existing puzzle. So you're just checking a simple that stuff in the first this one. And then for checking whether your elements, so now you need to do two types of checks on this. One is whether each of these elements are distinct or not, and this particular circuit is only for checking rows. It's only going to check rows if the rows are distinct or not. And the second one is you check whether the numbers are actually in range. That means are the numbers between 1 and 9, because that's what is allowed in your in this case you are checking whether the numbers are between 1 and n. So that's what is allowed in your Sudoku. So in order to do this, what you do is basically you are going to create two more templates to check these different conditions. So the way you write circum circuits is that whenever you have to check some conditions on top of your whatever it is problem that you're trying to solve. If it is not a small arithmetic condition, for example, if you have to check something, it's within a range. If you have to check like some other type of arithmetic constraints, then you should create separate templates for it. So here we have a template called distinct. So I'll go to that template first. In this template, you are defining something called distinct, and then you take a signal called, you take the signal to put in all an array of all the numbers that you're going to check whether all of these numbers are distinct or not. For this, there is another signal, another template called non-equal. This is the main template. This is actually the main and the only template that I want to explain here. Everything else is like, if you just go through the logic, you'll pretty much get it. The non-equal template takes two numbers and checks whether these two numbers are not equal. Now, there is no way in Circom to do something like not equal to because you don't have any like comparison and stuff like that, right? So what we do here in this case, this type of logic is that we create a signal called an intermediate signal. And every element, we say that we are going to create a multiplicative inverse of this element. Now, creating a multiplicative inverse is actually not R1CS compliant. So this is the rank 1 constraint system. This creating an inverse and things like that are not compliant with R1CS. That's why you have to use this assignment operator over here. So if you want to do something which is not a part of the constraint system, but Circom still allows you to do it. For example, in situations like this, where you have to check for equality of two numbers and make sure that they are non-equal, then you have to try and think of using some sort of this assignment operator in a way that it helps you create some mathematical conditions that will lead you to your final sort of expression. So in this case, we are going to create an inverse, which is like, we are saying that both the inputs we are going to subtract, and it is 1 divided by both of this. And we are assigning this to this intermediate signal called INV. And we take this signal and multiply this with the difference between IN0 and INV. And we constrain that this should be equal to only 1. So if this thing, if IN0 and IN1 turn out to be equal, then your circuit will fail here itself. Like this assignment will probably be something as a, I don't know, some number that this circuit is not able to resolve. So your circuit will fail, your constraint will fail here, because this number is not able to, whatever it is not able to resolve. So when it multiplies with this, again, this constraint is not met. But your Circom circuits will fail only at the constraints. It won't fail at assignments. So you want to make sure that whatever it condition that you want to check, you can try and add some assignments before that condition, and through those values that you get out of the assignments, you create your constraints. This is very important because in a lot of situations we will try to, this is just a non-equal situation, but there are a lot of other situations where we may come across some problem statements where we don't know how to do this kind of thing. And this is why this is one of the most, like, it's like a trick that they use, which is trying to create like this inverse, and then use that inverse for determining whether you can add your circuit meets that constraint or not. Now, yeah, this is the key part. Apart from this, everything is like everything else is pretty straightforward. So you create a component called non-equal, and then how you actually assign values to this component. This is also I want to show like a two-dimensional array. Maybe it's a bit confusing. So you assign this. You create you have already created a component. So you give the value non-equal to this component, and then for the first input, you send in of I, and then the second input you send in of j, and then you sort of keep repeating this entire thing within the loop. So this is a simple sort of you make sure that every number is distinct. The array of inputs that you're sending, all of these numbers are distinct. This is something, this is again, they have created a slightly more complex circuit using bits to check whether the number lies between 0 and 16. Because if you can the max number for if you have to take 3 bits, then the third one, the highest one that you can do with the third one is 8, but we have to have between 1 and 9. So that's why they have taken 4 bits, and they have taken this, they have created a circuit that makes sure that the number is basically lying between 0 and 16. And then to make sure that it is between 1 and 9, there is another logic which uses this bits for logic and make sure that the number lies between 1 and 9. So not explaining this because already a little bit over time. But yeah, so they have created these dependent circuits, distinct 1 to 9 bits for, and most important one is non-equal, which is what I want to explain. And then they are checking here for two conditions. One is the existing numbers are the same, and the second one that they will check is they will send the rows to the solution rows to check whether they are two things, whether they are distinct and they are in range. So both of these things we are checking, and if they meet the condition, then it is basically the you have proved that the solution is it's correct, like all of the rows are distinct, and you have you have solved the puzzle. So they said that you have to they ideally have to check every component, so they have to check rows and columns, but in this case they have just checked for rows, which also I think should work, because if all the rows are, no, I don't think it'll work, because they're just going to check all the rows are distinct. Oh no, I think it should work. If all the rows are distinct, then it's a proper solution. So yeah, also works. So yeah, there is one more Sudoku circuit that I'm going to give it to you as a homework, and that has a slightly different approach, but a similar problem statement that you have to try and so you see this another Sudoku circuit. This is a 4x4 Sudoku board, so a very simple one, and they have given you a question, example question, and they've given you a solution also. And using what you learned in this one, that is the logic, you have to write some part of the solution. So this can be a good homework, and yeah, I'll also try that. That's pretty much what I had. Thought I'll complete in 45 minutes, but take a bit. Any questions? Okay, yeah, Ovia, you have a question?
Hey, sorry, I just want to come back to your previous example on that lower bound and upper bound.
Mm-hmm.
So the solution really depends on how you give the lower bound and upper bound values. So if you give a lower bound that is higher than the upper bound, maybe the solution won't work.
Yeah,
So
yeah.
how do you enforce that? How do you enforce such checks on
I
the
don't think you can enforce in Circom. Maybe you can add, if you want, you can add another check which checks whether lower bound itself is like less than upper bound. Like you can use another circuit which is like less than or
yeah,
something. So you can add that, but that's not a part of the problem statement. The problem statement is that you get a lower bound, upper bound, and a signal. So you have to just see for the signal.
got it. And the it so whatever input arguments that you give to any of the circum functions, that it need not be private.
It need not be. It can be public also.
Mhm.
You can also give public signals. You can give part of, like, you, if you're giving three inputs, you can give one public, two private. By default they are private. So if we say signal input something, it's private. But when you're calling the template using a component, you can also make it public.
Okay. So what exactly are we trying to prove, and what is the witness part that we'll use later? So the witness is the actual arguments that you pass through the function.
Yeah. Witness is the actual argument. Correct. So they pass that input. So to generate the witness, they pass this input.json, which will be having the actual input, and they generate the witness through that. And
Hmm.
what that witness is supposed to do, that I don't know exactly.
Right. Yeah, even I'm just trying to piece all these bits of information together.
I
So
think after your session, maybe we'll have more clarity,
yeah,
like
yeah, yeah.
some, like, yeah, piece the things together.
Okay. Thanks, Kian. I really enjoyed this.
Yeah. Okay, awesome. Yeah. Thanks. Yeah. Thanks everyone.